Well, hello, hello, hello. This is Dr. Pete Mandik once again joining you. And or am I joining you? I am in a video, and I don't know what I'm doing except talking and looking at a camera right now. So maybe I'm joining you, and you're watching the video. That'd be good. And what we're going to do today is talk about space. This is our first lecture in our unit about metaphysics, and we're going to be talking about things like space and time and material objects and people, and um, a lot of what we're going to be talking about is stuff that you already are very familiar with, but maybe have taken for granted in many ways. So everybody knows about space and time. You know about where you are and how to get somewhere else. You know about what time it is and how to figure out how long it's going to be until lunchtime. But if you really start thinking in a philosophical way about questions like, well, what is space? Is space something? Is it nothing? If you took everything out of a box, including the air, if you've taken everything out of the box, is there nothing in the box? Or is there still something in the box? And namely, what's left in the box is space itself. Is space itself the sort of thing that has properties? A box has properties, an object has properties, but how about space itself? Does it have properties? If so, then it itself is a sort of a thing. What sort of properties might space have? Things have size. So, for example, this tobacco pipe has a size and it has a shape. How about space itself? Does it have a size? One possibility is that space is infinite, that it has the biggest possible size. And another possibility is that it is not infinite, it is smaller than that. Um, and how would you know which one it was, whether it was infinite or not? And one way in which we're going to talk about space and infinity is we're also going to talk about whether there's such a thing as infinitely small spaces. So when we talk about the size of space being infinitely large, we're saying that for any size, any distance, there's always going to be one that's larger. But what if we run it the other way? For anything that's short or small, is there also something excuse me, is there also something that's going to be smaller? Is there always something smaller? No matter how small you get, can you get smaller still? If so, then space is infinitely divisible. For every distance, there's a shorter distance. And one shorter than that, one shorter than that. And the alternate view is that there is a smallest distance. There's a point beyond which you can't get any smaller. So there's going to be some unit of distance such that there's no such thing as half that distance. So these are the sorts of things we're going to be talking about in this lecture. We'll save time for another lecture. But space and time they're really weird things. And at the same time, they're totally not weird. They're totally commonplace. Like if someone lost consciousness, like they're a boxer in a boxing match, and when they first wake up, one of the first things you ask them is, do you know where you are? Do you know what year it is? You ask them things about space and time. So we take that to be pretty basic. If you have your wits about you, you would know about that. But what if when they woke up, we asked them, what is time? They might say, I'm going back to sleep. What is space? What is space? So we're going to be focusing on some specific questions about space. There's lots of questions you could ask about space, like is space absolute versus relative? Is space a substance? Is space the same as nothing? But we're going to be focusing just specifically on the relationship between space and infinity. And those sorts of questions can be boiled down to two questions. Is space infinite? By which I mean, is it infinitely large? And is space infinitely divisible? Are there such things as smallest units of space? We might put this in terms of distances. If we're talking about space, is there a longest distance? And is there a shortest distance? If you say there is such a thing as a longest distance, then there's no distance which is larger than that distance. So then space wouldn't be infinite. If it was infinite, then that means for every distance that you could come up with, there's always going to be another one that's larger. And we could ask similar sorts of questions about time, by the way, although we're not going to focus a lot when we get to time. We're not going to be focusing so much on the stuff about infinity. But is there a longest duration? Is there an amount of time beyond which there is no longer duration? And we could also ask questions about infinite divisibility. Is there a shortest distance? We're nowadays very computer literate. Just about everybody I run into nowadays has a computer, at least in the form of a phone. Their smartphone is a kind of computer. And even if you have a so-called not smartphone, a stupid phone, it probably has a computer in it too. Cars have computers in them. Just about everything is computerized these days. Most refrigerators have like little computers in them. You can't do a whole lot with those computers, but there is a little computer in there dedicated to, trying to figure out how to keep your refrigerator cold. But if you're familiar with the sorts of computers you could play video games on, or the sorts of computer that's allowing you to watch this video right now, you're also probably familiar with the idea of a pixel. You're familiar with the idea that a computer screen is made out of a bunch of dots. And any amount of distance that you're going to represent on that computer screen has got to be made out of one or more of those dots. And there's nothing in that screen that could be smaller than one of those dots. So those dots are something like the shortest distance in space. Now, if space itself was like a computer screen, that means space itself would not be infinitely divisible. There would be such a thing as a shortest distance. It would be the pixel of space. Or since space is three-dimensional, and we're talking about volume instead of a plane, we're talking about volume instead of area. Instead of a pixel, it would be a voxel, the smallest unit in the three-dimensional space. Is space made out of voxels? Okay, so let's start with our first question about the question of the largeness of space. How big is space? Is space infinitely big? We're going to look at a couple of arguments from philosophers, one of which is an argument that says, yes, it is infinite, and the other one that says, no, it is not infinite. And this is kind of a warm-up exercise for the other question that we're going to probably spend a bit more time on, which has to do with whether there's such a thing as an infinitely small amount of space, and the closely related topic of whether there's an infinitely small amount of time. But let's get deeper into this. Is space infinite? So one philosopher that seems to have an opinion about just about everything is Aristotle. We've already been talking about Aristotle this semester, and Aristotle has an opinion about this. Is space infinite? Aristotle says no, and he has a philosophical argument for why space is not infinite. And you might think the argument is a little bit funny, but it's worth learning about anyway. And sometimes it's important to see the things that humans were wrong about. So anyway, here's how Aristotle's argument goes. He says the reason why space is not infinite is because if space was infinite, all right, let's start over again. I got tongue twisted. So question, is space infinite? Aristotle says no. So what he thinks then is that space is finite. So why does he think that space is finite? Well, he says that if space was infinite, then there wouldn't be a center to space. There's no center. And let's see if that makes any sense. So what does it mean for something to have a center? So let's take a thing that has a center. I'm getting a thing right now. Give me a moment. I'm getting a thing. Here we go. Got a piece of paper. Piece of paper. Let's get a better thing. I have this this cardboard coaster, and it says cheers on it. That's a happy thing. That's a good thing. And so this thing has a center. What does it mean for there to be a point on this thing, which is the center point? Well, it's the point that is equidistant from the edges. So this point right here is not the center because it's closer to this edge than some of the other edges. A point in the center is one that would be equidistant from all of the edges. That's what it means for that point to be at the center of this circular cardboard coaster. Okay, but now what if this circular cardboard coaster was infinitely big? That would mean that if you tried to head out towards the edge, you would never get there because there is no edge. So since there is no edge, it doesn't make sense to say that any point is any closer to the edge than any other point. So if space was infinite, then space wouldn't have a center. If space does have a center, then it must not be infinite. Now, Aristotle's argument goes like this. Space does have a center, but wait a minute, Aristotle, why do you think that? Why do you think space has a center? And he says, well, it's obvious that Earth is at the center of space. Assuming that it's obvious, assuming that it's even true, that Earth is at the center of space, it would follow that space does have a center, and so space cannot be infinite. Because what it means for something to be at the center is for it to be equidistant from the edges. But if space was infinite, then any point in space is as good a candidate as the center of space as every other. But you might say there's something funny about Aristotle's argument. Don't we know that Earth is not at the center of space? Haven't we learned that the sun is at the center? Well, no, we didn't learn that. We learned that if you want to come up with a representation of the way in which the planets orbit around one another, including the sun, you get a simpler representation if you put the sun at the center of that. It's simpler to model the motions of the bodies of the solar system as going around the sun than to model the sun as going around the Earth. If you wanted to, you could come up with a model like that, but then all the different orbits would be very curly. They'd be like a curly pig's tail, and that's not very neat. But what makes the neat one the right answer? It's actually kind of relative. You could choose one and say it's at the center, and choose the other and say that it's at the center. Probably if we looked for a scientific consensus about these, it would be that it doesn't make sense to say that either of them are at the center. And anyway, the sun is moving. It's moving around the center of the galaxy, and the galaxy itself is moving. So it doesn't make sense to say that any of these things is the stationary center around which the rest go. So that opens up that space is infinite. But just because we open it up that space is infinite, that's not actually an argument that space is infinite. What's an argument? What would be a positive argument for space being infinite? Let's move now to the philosopher Lucretius. And Lucretius has this argument about a dart. So suppose you were at the so-called edge of space. Just for the sake of argument, let's hypothetically grant that space is finite. That means space would have an edge, and it would be possible then to stand at the edge of space and then take a dart and throw it at the edge of space. What's going to happen when the dart gets to the edge of space? Is it going to either do this, which is to keep going beyond the edge of space, or is it going to stop as if it ran into a wall? Well, it's got to either be one or the other. It either has to keep going or it has to not keep going. That's just logic. And we might even say it's the principle of bivalence. It's got to be one or the other, or it can't be both and it can't be neither. Well, maybe it's this one. Could it keep on going? Well, we were hypothesizing that there's an edge to space. So if it were to keep on going, there has to be more space, but then that wasn't the edge of space. If it keeps going, then this line right here isn't the edge of space, because it has gone beyond it. It's gone beyond it to where? Well, more space. You might say, well, how about if the edge is here? But again, we could ask the question, what's going to happen when it gets to the edge? Is it going to go beyond that, or is it not going to go beyond that? It seems like if there's an edge to space, this can't be what happens. It can't be that the dart keeps going. So that would lead us to think that maybe this is the option, that when it gets to the so-called edge of space, it's going to stop. But wait a minute. If it stops, doesn't there have to be something that made it stop? This line of thinking is very similar to something that is associated with the philosopher Leibniz. Leibniz is somebody who keeps coming up in our lectures, and we'll see Leibniz again and again. Leibniz is very famous for a whole bunch of things, and one of them that's relevant right here and now is something called the principle of sufficient reason. One way of putting the idea of the principle of sufficient reason is to say that anything that happens has to happen for a reason. Another closely related idea, or different way of putting the principle of sufficient reason, is to say if something happens, there has to be something that made it happen. So here's something that's happening. A dart is moving and then it stops. What made it stop? Well, if this is the edge of space, then that means there's nothing beyond this line. But can you get something from nothing? Can nothing do anything? Can nothing make this stop? We are familiar with darts that fly through the air and then stop, but in all those cases, it's usually because the dart ran into something, like a dartboard. Why did that dart stop? Well, because it hit the dartboard. That's why it stopped. Or it hit me right in the middle of the forehead. That's why it stopped. Ow. Usually when we see a dart fly and then stop, there was something that made it stop. And you might say, that always makes sense. You can't get something from nothing. For everything that happens, there has to be some reason why it happened. There has to be something that made it happen. If the dart stopped, there had to be something that made it stop. But by hypothesis, there was nothing here, so there's nothing that could have made it stop. So you might say it can't stop. It would have to keep on going. But now we're back to this situation. This situation, it keeps on going, is inconsistent with the proposition that this is the edge of space. So one way of seeing how Lucretius's argument is supposed to work is that it's a sort of argument known as a reductio ad absurdum. A reductio ad absurdum, a reduction to absurdity. You take something and you argue against that something by saying that, well, if we think about it, we'll realize that that something would lead to absurdity. So we start by supposing, just for the sake of argument, that space is finite, and then we show, at least according to Lucretius, we show that if space was finite, then you would be led to this absurd situation. You'd be led to this logically contradictory situation. But there can't be real logical contradictions in nature, so therefore, the thing that we were hypothesizing for the sake of argument turns out to be false. We showed that something is not true because if it were true, it would entail a logical contradiction. It would entail an absurdity. And that, according to Lucretius, is supposed to be why space is infinite. Okay, like I said, we are looking at the question, is space infinite? In part just to kind of get warmed up for the main event. The main event is going to be the question of whether space and also time are infinitely divisible. Or in other words, is there such a thing as a shortest distance or shortest duration? And the arguments that we're going to examine in the rest of this lecture are going to come from two ancient philosophers. You may have heard of one or both of them. You may have heard of Pythagoras, or at least you've heard of the Pythagorean theorem in one of your math classes. And then we're also going to talk about some arguments from the philosopher Zeno. And these are both relevant to the question of whether there's a shortest distance let's start with Pythagoras. So you're probably familiar with Pythagoras, at least in the form of the Pythagorean theorem. And you know that the Pythagorean theorem goes something like a squared plus b squared equals c squared. And you might even remember what the a and the b and the c are supposed to stand for. These are the sides of triangles, in particular right triangles. If you have a right triangle and the hypotenuse of that triangle is c, then the other sides of the triangle are a and b. And according to the Pythagorean theorem, if you square the distance of a and add it to the square of the distance of b, that will equal the square of the distance of c, the hypotenuse. Here's a really easy example to remember. If the triangle was 3 units high and 4 units wide, then you could square 3 and 4 and get 9 and 16 respectively, and you add those together and you get 25. The square root of 25 is 5, and 5 would be the hypotenuse. If you had a stick that was 5 feet long, you could stick it in a box that was 3 by 4, and it would just go across the diagonal of the box. Okay, so that's the Pythagorean theorem. You're familiar with the Pythagorean theorem. Pythagoras was very interested in the relationship between number and shape, and he was interested in the question of whether reality had smallest units. And he wanted to believe that it did have smallest units. But that didn't fit very well with his famous Pythagorean theorem. One way we can think about the Pythagorean theorem is how would it apply to an isosceles right triangle. An isosceles right triangle is where the sides that are on either side of the right angle are equal to each other. So if there is an isosceles right triangle whose sides are n, then the hypotenuse is going to be n times the square root of 2. And what if the sides were just 1? Well, then the hypotenuse would have to be n times the square root of 2, which would just be the square root of 2. But now, the square root of 2 is not a whole number. The square root of 2 is not something that you could represent in whole number units. It would be something that is greater than 1 and smaller than 2, but that wouldn't be a whole number. But if there... So, I mean, part of what we're saying is that if there were such a smallest unit, which is n, then all... Like with respect to space, the smallest distance would be n. Then space would have to be made out of pixels, the size of which was n. And the next distance larger than n is 2n, 2 times n, otherwise known as 2 of the smallest units. But that would be way bigger than this hypotenuse. So, and not only do these remarks apply to the smallest right isosceles triangle, but it applies to all right isosceles right triangles. In other words, there just couldn't be right isosceles triangles if space was discrete, if space came in smallest units. Here's another way of thinking about it. If space came in smallest units, and there were right isosceles triangles, well, how would you make them? How would you make them out of the smallest units? Would you make it like this? So here I've got a right triangle that is 4 units wide and it's 4 units tall. But now how many units is that hypotenuse going to be? Like here's 4 units, but you could see the spaces between these 4 units are bigger than the spaces here. That seems like cheating. That's not really how it would work. That's not a right isosceles triangle that's also made out of smallest units. Well, would you do it like this? Cram an extra unit in there? Well, no, that's wrong also. That's still not going to be a right isosceles triangle that's perfectly made out of these so-called smallest distances. Hopefully you can see that if there are such things as right isosceles triangles, then space would have to be continuous. Now, you might say maybe there aren't actually any triangles, because you recall in the lecture about rationalism, we were talking about the strange proposition that maybe you've never ever seen a triangle. And maybe the reason you've never ever seen a triangle is that there just aren't such things as triangles. But okay, so there couldn't be triangles. Not, it's impossible for there to be triangles. Nothing, not even a region of space could be triangular. Well, that's interesting. You might say there have to be right isosceles triangles. Maybe things that are made out of matter are always lumpy and never straight, but couldn't space itself have straight lines in it and regions in which there are perfect triangles, regions of which are right angled triangles, regions of which are right isosceles triangles? And wouldn't the hypotenuse of some of those then be exactly equal to the square root of 2? If all that's true, then space would have to be continuous. And one way of saying that space would be continuous then would be to say that space is infinitely divisible. There's no such thing as a smallest unit of space. Every time you have a unit of space, there's always one unit which is smaller. Let's shift over to Zeno. Zeno is going to probably give you a headache, to be quite frank. Zeno is someone who is very frustrating, but his arguments are so interesting that it is worth studying. But one quick sneak preview before we get deeper into Zeno of what Zeno is trying to say is that Zeno is going to focus on motion. We've been talking about space and whether space is infinitely large and infinitely divisible. But one way of thinking about space is it's that which through you move. When you move, you're moving through space. Motion just is a change of location over time. That's what motion is. So if you want to study space, maybe one way to study space is to study motion. And we're going to look at a bunch of arguments from Zeno that are supposed to add up to the proposition that motion is impossible. And you might say that's ridiculous. Obviously motion is possible. Mandik, we see you're moving your head around, you're moving the Kleenex up to your nose because you've got allergy problems. Your mouth is always moving, Mandik. Obviously there's motion. What's with the Zeno guy? What is he after? And one interpretation of what Zeno is after is that he was a student of the philosopher Parmenides, and Parmenides believed that all change was an illusion. In fact, all number was an illusion. There was nothing except just this one thing, which we could call the one. And all change and all variety and all multiplicity were just illusions. The true, real reality was singular and solitary and eternal and unchanging. And so he was arguing against motion as part of a larger project of proving that Parmenides was right. Another interpretation is to show that the way we think about motion must be wrong. There must be some fundamental flaw in the way we think about space and motion. And the reason to study Zeno is not to convince yourself that we don't move, but to show that we're making assumptions about motion that lead to absurdity. And so we should reject those assumptions and try to figure out a better theory of what motion is. Before we get deeper into the Zeno arguments, let's take a little bit of a break, well, at least a break for me, not a break for you, and study some study questions. So here are 2 study questions. There's going to be 2 more later on, and even later still will be the answers to the questions. Study question number 1. Which of the following is a problem that Pythagoras ran into concerning the idea that both space and matter are composed of indivisible units? A, if you started counting the units, you might fall asleep before you finished counting the units. B, if the units are beans, they should not be eaten, for beans are fart inducers, and farting diminishes the soul. C, it seems impossible that each right triangle has sides with lengths measurable as whole numbers. D, how big are these units? Too big, maybe? E, if the units existed forever, then they were never created, which is absurd. By the way, I'm not going to tell you the right answer right now, but I will tell you that answer B refers to a true fact about Pythagoras and his followers. Pythagoras was kind of a cult leader, and he had a lot of followers, and one of the things that he taught the followers was not to eat beans. And his reasoning was exactly this thing that's written here in B, that beans make you pass gas, which will make you lose your soul, at least a little bit of your soul. You don't want to lose your soul, so stay off of the beans. Question number 2, what's the conclusion of the following argument of Aristotle's? The earth is at the center of the universe. However, an infinite being cannot have a center. So that's an argument, at least those are premises of an argument. What's the conclusion of that argument supposed to be? Is the conclusion supposed to be A, space is finite, B, space is infinite, C, time is finite, D, time is infinite, E, love is infinite, or finite, whatever. Love is love, bro. Okay, let's talk about Zeno and infinity. And by the way, that's a little picture of Zeno, and he's leaving the temple, and he's going to go walk over to an olive tree. And in a little bit, we're going to hear a story about what's puzzling about this very simple act of going from one place to another, why that might lead to a paradox. Now, here's a reminder that we're talking about the question of whether space is infinitely divisible or not, and there's a closely related question about whether time is infinitely divisible or not. If space and time are only finitely divisible, that means that they are discrete. That means they are chunky. They come in chunks, and the chunks don't themselves have any smaller chunks. On the other hand, if they are infinitely divisible, then they are continuous. They're not chunky, but they're smooth. Space and time would be smooth. Any division that you could introduce could itself be divided, and divided again, divided again. There's never a smallest unit. There's always a unit that's smaller than that one, and a unit smaller than that one, and so on for infinity. So Zeno is going to have some arguments that are about motion, arguments in which he shows that there's some kind of paradox, and these arguments are going to make assumptions, and some of the arguments are going to have slightly different assumptions from some of the other arguments. We can group the arguments in terms of what assumptions they make. In particular, we could group the first 2 arguments as assuming that space is continuous. And the second 2 arguments are going to assume that space is discrete. Now, this is all going to add up to one big giant argument from Zeno that motion is impossible. And it goes something like this. And I'm talking now about the big argument. Either space is continuous or discrete. It has to be one or the other. It can't be both. And it can't be neither. It's got to either have smallest units or it doesn't have smallest units. If it does have smallest units, then that leads to absurdities that are spelled out in the argument of the arrow and the argument of the stadium. If, on the other hand, space doesn't have smallest units, it is instead what we call continuous, then that leads to the absurdities spelled out in the Achilles and the Tortoise argument, and also the argument that we're going to call the dichotomy. So, we could represent Zeno's big argument, of which these 4 other arguments are just parts, like this. We've got one premise that says either space and time are continuous or space and time are discrete. And then we have this other premise that says if space and time are continuous, then motion is impossible. And that's because of the Achilles argument and the dichotomy argument. And if space and time are discrete, then motion is still impossible. And that's shown by the arrow argument and the stadium argument. And then the master conclusion is that motion is impossible. And you might say, this is idiotic. Obviously, motion is possible. Okay, well then we can work our way backwards. Given that motion is possible, there has to be a problem here. Where is the problem? Is the problem in assuming that space and time are discrete? Is that the problem? Okay, well, then we have a solution to the problem. Stop assuming that. Or maybe the problem is the assumption that space and time are continuous. If that's the problem, now we have a solution. Stop assuming that one. But the argument itself looks like it's a good argument in the sense that it's valid. If these premises are true, it would seem like it's going to lead to the conclusion that motion is impossible. And that's a valuable thing that Zeno has helped us realize. But you might not want to conclude that motion is actually impossible. Although I do meet students that they like that. They're like, yeah, right, yeah, motion's impossible. Most students look at this and say, right, that obviously motion is possible, so there has to be something wrong somewhere else. Is it with the assumption of discreteness? Is it with the assumption of continuousness, or something else that's hidden we haven't discovered yet? But nonetheless, there has to be a problem. But let's go through the little arguments now, starting with Achilles. Achilles and the tortoise. Not just Achilles, but Achilles and the tortoise. Okay, so there's going to be a race, and in this race, it's going to be Achilles racing a tortoise. And one thing you know about tortoises is that they're like big turtles, and they're pretty slow. And you might know that Achilles is like an amazing athlete, and he's pretty fast. And if there's going to be a fair race between Achilles and a tortoise, you're going to have to give the tortoise a head start, right? Like a huge head start. But now, most of the distances that you would have the race, and most of the head starts that you would give the tortoise, wouldn't those be ones in which Achilles could eventually catch up and then still beat the tortoise? Isn't it possible that even though the tortoise had a slow start, that Achilles could overcome the tortoise, that Achilles could pass the tortoise and still lead the race? Well, Zeno says, arguably, it's impossible. Now, that might seem really weird to you, and it's supposed to seem weird to you. It is supposed to seem really weird to claim that it's impossible. But let's see how this is supposed to go. Okay, so suppose this is Achilles, and the turtle was at this point right here, and Achilles wants to catch up to that point. Okay, right? So if Achilles is going to win the race, that means after the race starts, any point that Achilles is at, I'm sorry, oh, I got tongue twisted again. After the start of the race, if Achilles is going to win the race by passing the turtle, that means that any point the turtle was at, Achilles is going to get to that point, right? Okay, so here's a point that the turtle was at. If Achilles is going to get to that point, it's going to happen over some amount of time, right? He's not running infinitely fast. But now, by the time he gets to that point, the tortoise will have moved on. You following the scenario so far? You don't need to understand the whole argument. Just try to understand this one part right now. So if the tortoise has a head start, there's some point at which the tortoise is, and Achilles is going to have to get to that point. But that's going to take a certain amount of time. And in that time, by the time Achilles gets to that point, the turtle will have moved on to some other point. So now what? Well, if Achilles is going to win the race, Achilles needs to get past that point, the new point that the tortoise is at. So there he goes. He runs from that point to this point. There's a whole bunch of Achilles here just to show like Achilles at different moments of time. Okay? So we have moved to a later moment in time. Achilles wants to run to this point where the turtle had gotten to. But the turtle has once again moved on to yet another point. And so Achilles has to move to that point too. But again, the turtle will have moved on. And you might say, so what? Turtle is slower than Achilles. No matter how big of a head start the turtle gets, there's got to be a size of the racetrack such that Achilles will pass up the turtle. So let's pick one of those racetracks and talk about it. Let's picture a racetrack that you think it's pretty obvious that Achilles is going to win the race. Suppose it's a 1 mile race, and Achilles runs as fast as the fastest human being that's ever run, and the tortoise runs as fast as the average tortoise. Okay, and it's a 1 mile race, and we give the tortoise a head start of 10 feet. All right? Will Achilles win the race? You might say, yeah, I can't do math, but it's obvious. If we're talking about a mile versus 10 feet, and the fastest human versus an average tortoise, obviously Achilles is going to win this race. Okay, now let's focus on that race and ask, how does Achilles win the race? How is it even possible? Because for any point that the tortoise is at after the start of the race, by the time Achilles gets to that point, the tortoise will have moved to some other point beyond that. And now Achilles has to get to that point. But by the time he gets there, there's some other point that the tortoise has gotten to. And on the assumption, remember we're assuming for the Achilles and the tortoise, on the assumption that space and time are continuous, there's always going to be some additional distance that Achilles has to run. And there's going to be some additional time that it takes for him to do it, during which the tortoise will have gone farther. And you might say, but aren't these getting smaller and smaller, these distances? Yeah, they might be getting smaller and smaller, but the conclusion of this argument, Achilles and the tortoise, is that the tortoise will always be able to be ahead of Achilles. Since space and time are continuous, there's no such thing as a smallest unit of time or a smallest unit of space. So there's always going to be some amount of time in which the tortoise is able to go a little bit further down the line. And so that when Achilles gets to that space, the tortoise won't be there anymore. So Achilles will always be behind the turtle. Achilles is doomed to lose the race, or at least doomed to not win the race. So that's how the Achilles argument is supposed to go. And you might say, that's so confusing. It's what? It doesn't make any sense at all. Obviously, Achilles is going to win the race. Yes, I'll grant you that it's obvious that Achilles is going to win the race. But now explain how the following is possible. If we assume that space and time are continuous, doesn't it follow that no matter where the turtle is, that before Achilles gets to that point, the turtle will have had enough time to go somewhere else? Isn't that possible? But doesn't it follow then that if space is continuous, that there's always going to be enough time and enough space, no matter how small, isn't there always going to be enough for the turtle to go somewhere else and thus have gotten away from where Achilles is going to wind up? And doesn't it follow from that then that Achilles never passes the tortoise? Let's move on to the dichotomy. In some sense, the dichotomy is simpler. Achilles and the tortoise has two characters in it, Achilles and the tortoise. For the dichotomy, we just need one character. So there's Zeno. Zeno is going to walk from the temple to the olive tree. Now, there's a couple ways we can think of this argument. One, we can think of the argument like this. So, before Achilles gets all the way to the olive tree, he first has to get to the halfway point. And before he I'm sorry, this drawing is not the best drawing for this. I just realized this is a bad drawing for representing this. But I'm gonna stipulate a small change about this drawing. Imagine that imagine that Zeno is walking backwards, okay? So he's doing a moonwalk. He's moonwalking from the olive tree to the temple, okay? So he wants to go all the way from the tree to the temple. Now, before he gets all the way to the temple, won't he first have to get to the halfway point? Okay, well, you might say, yeah, so what? All right. But now, before he gets to the halfway point, wouldn't he first have to get to the halfway point, the so-called quarter way point? You might say, yeah, I guess so. I see that. Well, and before he gets to the quarter way point, wouldn't he have to get to the halfway point before that? So not only before he gets to the halfway point, he has to get to the halfway point before that, but before he gets to that point, he has to get to the halfway point before that. Isn't that true? Yeah, okay. And doesn't he have to get to the halfway point before that one? And before he does that, he gets to the halfway point before that one. And before he does that, doesn't he have to get to the halfway point before that one? And if we are assuming, as I said, we are assuming for the dichotomy argument that space is continuous, isn't there an infinite number of such halfway points? So how many journeys does he have to take before he even gets to the halfway point? And the answer is he has to take an infinite number of journeys. Now, how can that be? How can he take an infinite number of journeys? How can he take an infinite number of journeys before he even gets to the halfway point? How can he take an infinite number of journeys before he even gets to the halfway point to the halfway point? How can he do that? Here's another problem. Isn't there an infinite number of journeys? Isn't there an infinite number of steps right before any step that you pick here? Before he gets to that, he has to do the one before it. If he's going to start this journey from the tree to the temple, he has to first cross the smallest distance. But there is no smallest distance on the assumption that space is continuous. So he can't even start this journey. Now here's another way of representing it. If instead of him walking backwards from the olive tree, he's walking forwards from the temple, we might say, yeah, okay, maybe he starts the journey. His first step is this big leap from here to here. But there's still a halfway point beyond this and halfway point after that one. So yeah, after he goes halfway from here to here, wouldn't he have to go halfway? But before he did that, he has to go halfway. So you can do the dichotomy argument in terms of a journey whereby it looks like it's impossible for him to take the first step. If we start over here, there's an infinite number of smaller steps, none of which is the first step. Or if we start over here, there's an infinite number of steps, none of which is the last step. So either he starts over here but can't really start the journey, or he starts over here and can't really end the journey. Here's another way of putting the problem with the dichotomy. If he is able, in a finite amount of time, to travel from the temple to the olive tree, or the olive tree to the temple, this has to be a finite distance. If it's a finite distance and space is continuous, then those distances are made out of infinitely small sub-distances. But now, how big is infinitely small? An infinitely small distance, is that bigger than 0 or equal to 0? If it's equal to 0, then no number of them would add up to this finite distance. If you had an infinite number of distances, all of which are equal to 0, then they're just going to add up to 0. 0 plus 0 equals 0, 0 plus 0 plus 0 equals 0, 0 plus 0 plus 0 plus 0 equals 0. 0 plus any number of zeros is still going to be 0, even if it's an infinite number of zeros. So if this divides up into infinitely small distances, and what it means to be infinitely small is to be 0, then an infinite number of them won't add up to this finite distance. So you might say, okay, then these these infinitely divisible distances, these infinitely small distances, have to be greater than 0, because they all add up to something greater than 0. So they themselves would have to be greater than 0. But now, how can they add up to something that's less than infinity? No matter how small a number is, if you add that to itself an infinite number of times, isn't the result going to be infinitely large? How would we get something that is simply half a mile? Both the Achilles and the Tortoise argument and the dichotomy argument assume that space is continuous and then show that that's supposed to lead to absurd situations where, for example, Achilles just can't catch up to the tortoise, or Zeno just can't get from point A to point B. You might say, well, let's try the other assumption. How about we assume that space and time are discrete and see what happens? Well, now let's talk about the arrow and then the stadium. So here is the arrow argument. Assuming that space and time are discrete, then one way of thinking about an arrow and its relationship to space and time is very much like video game graphics, especially in really old school video games. So here's an arrow made out of some big pixels. And time is also going to be discrete. And here's the arrow flying through space. So down here, we've got the time represented. And now the arrow is moving, and also time is moving. Question: when does the arrow move? Let's do that again. So I've got a little movie here we're watching. A movie about an arrow. At the beginning of the movie, it is 1, 0, 0, 0, 0. And then we move in time 1 unit. And the arrow moves in space 1 unit. That's what motion would look like in a discrete space-time. There's the smallest unit of space. There are smallest units of matter that take up those smallest units of space. The arrow is made out of a collection of those units, which take up a collection of pixels. And what it means for it to move is for it to be at those different locations at those different times. So at 1 minute and 1 second, it's at that location. At 1 minute and 2 seconds, it's at this next location. And at 1 minute and 3 seconds, it's at this next location. But when does the arrow move? Well, if there's an answer to that question, when does the arrow move, the answer has to be given at a time, right? Like, when did you eat lunch? Oh, I ate lunch at 12:30. Okay, so that's the time you ate lunch. When does the arrow move? Well, it has to move at a time if it moves. Well, which time was it? Was it this time? Is that when the arrow moved? Well, look at that time. There's just an arrow sitting there at that time. Well, look at that time. Is that when it moved? Did it move at that time? It doesn't look like it's moving it at that time. Nor did it move at that time. Nor did it move at that time. It's not moving at any of those times. And those are the only times that exist. If it's not moving at any of those times, and those are the only times that exist, then it can't be moving at any time. There's no time in which it moves, so therefore it doesn't move. Now you might say something like, the answer to the question, when does the arrow move, is that it moves over time. The moving of the arrow just is the fact that it is at different locations at different times. That is motion. So when is it moving? It's moving across these two times, or it's moving in between? Well, it can't be moving in between because there is no in between. On the hypothesis that space and time are discrete, then that means that there's no time in between this time and that time. So it can't be moving in between those two times. Can it be moving during those times? Well, these two times are the only times there are, and it's not moving at this one, and it's not moving at this one. So how can it be moving at both of them? Look, if I'm not in this place and I'm not in that place, then I can't be at both places, right? If I'm not in Pennsylvania and I'm not in California, then I can't be at both Pennsylvania and California. So similarly, if this arrow is not moving at this time and it's not moving at that time, it doesn't make any sense to say it's moving at both of them. So in summary, it looks like if space and time are discrete, then the answer to the question, when does the arrow move, is never. It never moves. But then that's like saying that it doesn't move at all. And that's like saying motion would be impossible. The stadium argument is very similar to the arrow argument, but it's a bit more complicated. Imagine that you are the king or the queen of your country, or the president, and you're watching a military parade, and there's some soldiers, and they are going to be marching in formation. So you're looking down from your presidential booth, you're looking down at a bunch of soldiers, and I've got 9 soldiers arranged such that I've got three soldiers in this row, 3 in this row, and 3 in this row. Okay? And some of the rows of soldiers are going to move in one direction, and some are going to move in the other direction. Okay? So instead of the arrow moving like this, we've got a couple different rows of soldiers, and they're moving in a couple different directions. Okay? So the blue row, A1, A2, A3, is going to stay put. B1 and B2 and B3, that row is going to move to the left, and C1, C2, and C3, the golden row, they're going to move to the right. At 1 minute and 1 second, they've moved like this. Question: when did soldier B3 pass soldier C2? You might say, oh, what? Wait, what? You might say that, what? Well, let's think this through. Okay, so here is where soldier C2 is right now, and C2 was moving from the left to the right. Here is where B3 is, and B3 was moving from the right to the left. You could see now that B3 is past C2, and you might infer that they must have passed one another. Since one is now past the other, there must have been a point and a time when they passed one another. But when was that? When did they pass one another? There's only 2 times to choose from. We're assuming that time is discrete here, so there's only 2 times to choose from. We could choose either this time or this time. Well, at this time, B3 is not B3 is not past C2. So time of 10000, B3 is not past C2. So that's not when it happened. Seems like it hasn't happened yet. And the only other time to choose from is the very next time, but now it looks like it already happened. B3 has already passed C2. So when did B3 pass C2? Answer, at no time. B3 never passed C2. But then how did B3 get there without going past? That seems absurd. And so you might say then, again, if space and time are discrete, then motion is impossible. Motion is just absurd. So we've got these four arguments from Zeno, and they all add up to the conclusion that motion is impossible. If motion was possible, it would either have to be continuous or would have to be discrete. If we're continuous, you lead to these absurd situations of Achilles never finishing the race, or Zeno never finishes his journey, or Achilles never wins the race. If it's discrete, you get the absurdity that the arrow doesn't move, or that the one soldier never passes the other soldier. So therefore, motion is impossible. We've got another version of a reductio ad absurdum. Now, what's the point of all this? Why even think about this? Well, one answer to that question is that it helps us clarify what we mean by things like space and motion and infinity. And in the history of mathematics and physics, it's been enormously useful to think about these sorts of problems. Another answer to this question is that maybe this is leading us to a further and deeper philosophical truth. The philosopher Immanuel Kant argued in his huge book, The Critique of Pure Reason, that if we think about certain metaphysical puzzles like this, where it looks like you've got equally strong arguments for one conclusion and equally strong arguments for the opposite conclusion, that would lead us to believe that the things we're talking about don't really exist. They don't have an existence independently of our minds. So that even space itself exists in the mind. And what we have now is a form of idealism. This is what Kant called his transcendental idealism. Specifically, it's the view that everything intuited in space and time, therefore all objects of any experience possible to us, are nothing but appearances, that is, mere representations. We had discussed in an earlier lecture, back when we were talking about skepticism, that one possible solution to skepticism is maybe to adopt idealism. There's this Kantian line of thought that says that maybe a kind of idealism should be adopted, because if you assume the opposite of idealism, you assume a kind of realism, then you're led to these like weird paradoxes and absurdities. If space and time are really real and exist independently of the mind, then you get weird contradictions like that the arrow moves and doesn't move. You get weird, absurd cases like the Achilles never wins the race against the tortoise. Okay, here's two more study questions. We already had questions 1 and 2. Here's questions 3 and 4. 3. Which of the following is the clearest example of a continuous series? A, the whole numbers between 2 and 17. B, the musical notes in a major scale. C, the real numbers, that is the rational and irrational numbers between 2 and 17. D, the letter grades you can earn in this class. E, the times shown on a digital wristwatch. And question 4, which of Zeno's paradoxes relies on the assumption that space is discrete? Is it A, Achilles and the tortoise, B, the dichotomy, C, Thomson's lamp, D, all of the above, or E, none of the above? And here are the answers to all 4 of the study questions for today's lecture. Number 1 is C, number 2 is A, number 3 is C, and number 4 is E. And that brings us to the end. So that's something that Zeno said was impossible. It's impossible to get to the end. And look, we did it. We got to the end. So what does that show us? I don't know. It's the end. I'll see you later. Bye-bye.